All right, hello and welcome everybody. Before we begin, very nice and sharp at 8 p.m., let's do a quick audio test. Okay, then let's see. Everything is ready. And let's begin. Right, so give me a second. Let me just put everything in the right places. And here we go. So, hi, and welcome everybody back to our live streaming, live solving session for Homeschool.Asia. So, today we'll be solving the entire paper for IGCSE Physics, subject code 0625, summer 2025, paper 4, set 1. All right. So, for our session today, we are going through the entire paper and we will go through each and every question in detail. So, for those of you who find any questions that you want to ask, please feel free to ask in the live comment section. And our physics teacher, Mr. Naran sir, will go through your questions in a first come, first serve basis. And we will try to answer your queries as much as possible as long as they are within the IGCSE Physics syllabus. So, once again, if you do have any issues, if any queries for us, please feel free to ask in chat, okay? In chat, Narayan sir will be looking through it very, very intently, and we will be filtering through the questions. Please make sure the questions are IGCSE Physics and is relevant, okay? So, with that said and done, let's begin today's solving session. And here we are. right? So for those of you who can see, hello and welcome. Let's begin with question number 1. But before we begin, once again, please take note, right? There are some important information that's given in our exam paper. So for instance, we do know over here, right, that G, the acceleration from free fall is 9.8 meters per second squared, right? So please don't use 10, please don't use 9.81, use 9.8 as given in our syllabus, all right? Also in this paper that I'll be solving, everything will be solved within two significant figures, all right? So if you are unsure how that works, one of the questions I will show you guys how we solve these questions to two significant figures, how it works, and hopefully this will cause you guys much less confusion about significant figures and such, okay? Rounding up or rounding down, so on and so forth, all right? So this paper is paper 4.1. It is 1 hour 15 minutes long. So if you have any issues of doing this right, you can print out the entire paper and work together with me to solve each and every question. Okay? Do take note, bring yourself a ruler, and also for the parts that requires you to draw in the paper, use a pencil to draw. I currently use a Wacom, so I can't say it's a pen or pencil, but for you who are solving the paper, please use a pencil, okay? Now, let's begin today's paper, starting from question number 1. Okay, so question 1, usually for an IGCSE paper, it's usually a question on kinematics, speed, distance, velocity, accelerations, and displacement, so on and so forth, right? So let's start with question 1A. So for 1A, right, as you can see, it wants you to circle the vector quantities in the list, all right? So let's take a look at all these quantities here. Acceleration, so what's a vector quantity? A vector quantity is a quantity that has a magnitude and a direction, okay? So pardon the horrible handwriting. I'm still not used to the Wacom, even though I have done so many videos already. All right, so it has a magnitude and a direction. So let's take a look at all these quantities here. So firstly, acceleration. Acceleration has a magnitude, of course, and it also has a direction. So you accelerate either forward or backwards, don't you? So acceleration is a vector quantity. All right. Now, number 2, mass. Mass is essentially a measure of how much substance is there in the body. So it's only positive mass, there's no negative mass, as we do off in our syllabus. So mass is not a vector quantity. Speed, same thing. There's only is a measure of how fast something is going, but it doesn't tell you the direction the thing is going. So speed is also not a vector. Time, same thing, it only goes forward, it doesn't go backwards. So it's only these three are so-called scalar quantities, which only has a magnitude. So last but not least, velocity. Velocity is similar to speed, but it has a direction. It tells you where is it moving. So velocity is also a vector quantity. All right, so as long as you circle both acceleration and velocity, you should get your full 1 mark. All right, pretty simple, right? Let's move on to question 1B. Okay, so for 1B, we can see over here this is a graph, right? And this is a speed time graph of a train traveling from station A to station B. All right, so as you can see over here, the graph starts here from 0, 0. The graph have a nice long straight line all the way up to here. We will find this value later at this time, and it moves off here at a constant speed, and then afterwards it goes back down again. This is a deceleration. This is acceleration, this is constant speed, this is deceleration. Okay, so let's write it down. Acceleration, constant speed, and this is deceleration. All right, so do remember, in a speed time graph, if the gradient, or should I say the slope, right, if it's going upwards like this is acceleration. And if the line is horizontal like this and is parallel to the time over here, which is the x-axis, this is constant speed. And when the line slopes downwards like this, right, this is deceleration. Okay, right, let's take a look here. For 1b part 1, we are to state the maximum speed of the train. Okay, so maximum speed is basically the highest point where this line is holding, is moving, is drawn. Okay, and you can see, right, in this graph, the highest point, should I say the greatest value of this graph is at this constant speed area over here. So for this, right, let's find out what's the greatest speed. So C50, here's 60. There are 10 divisions on this graph. So this is 51, 52, 53, 54, 55, 56, 57, 58, 59, and 60. So we are right here. This is 56, right? 56 meters per second. This corresponds to the constant speed of the graph, which is also its greatest speed. So once that's done, let's come down here and write 56 meters per second. Okay, please remember to write your correct reading as well as the correct units. All right, it's meters per second, not donkeys per second. Okay, then that will get you your full 1 mark. Okay, now you have found out the maximum speed. Question B, part 2, wants you to describe the motion of the train between stations A and stations B. So as stated before, you can see over here, right? From here to say around here, this part, right? Sorry for the not so straight line. From here to here, the train is accelerating. Then from here to this point over here, okay, the train is traveling at maximum speed, but it's constant. And then from here to here, right here, okay, the train is decelerating back to zero, back to not moving. So the train accelerates, move at constant speed for a while, and then decelerates back to not moving, back to not moving at all. Okay, so anyway, hello, we have a guest over here. All right, so say hi to our professor. Professor Lily is over here. All right, so anyway, let's take a look at this. All right, so we are to describe the motion of the train between stations A and stations B. Okay, let's take a look here. Right. Okay, so basically, let's write down what exactly is happening over here. Okay, so the train accelerates constantly to the maximum speed of 56 meters per second. That is our first part, right? Okay, from 0 to 80 seconds. So this is 80 seconds right there, over here. Okay, and then it maintains this constant speed, this top speed, right, from 80 seconds all the way to here, which is 480 seconds. Okay, from here to here. And then from 480 seconds to 530 seconds, it decelerates constantly until it reaches station B and comes to a rest. All right, so if you write down that, okay, if you write over here that, you know, the train accelerates, right, it accelerates first, okay, and then maintains its constant speed, and then decelerates the train, right, you should get your full 2 marks. All right, Professor Lily, please excuse me, I need to write down something. All right, so say hi to the chat. I'll put you away. All right. So once you have written those 3 points, you should get your full 2 marks. Okay. Right. Let's move on. Now let's move on to question B, part 3. Calculate the distance between stations A and station B. So in a speed time graph like this, right, we are to find, if we want to find the distance traveled by the train, we employ something called area under the graph. What does that mean? The area under the graph is basically, we are to calculate the entire area of this entire trapezium over here. Okay, so excuse me, please do not say hi to the camera. Let's push you away. All right, so the area under the graph is basically this entire chunk of the trapezium. So in order to find the area under the graph, let's do this, okay? So we do know the distance traveled to be equals to area under graph. All right. And the area under graph over here is simply the area of the trapezium over here. So let's just write down trapezium. All right. So what is the area of a trapezium? Is usually half of the 2 parallel sides, which is, as we see over here, we need to take half of this part plus this part. All right. So this part over here, right, is 480 minus 80. And this should be 400. And the longer side down here is 530. So let's write that down. So half plus the parallel sides and multiply by the height. All right. So area under graph should be equals to half times sum of parallel sides, which is 530, which is the lower part, plus 400, which is the upper part. And then we multiplied it by the height. The height is basically 56 meters per second, 56, right? Okay. And doing the mathematics, we should get 26,040. Okay, you are now tempted to write this as our answer, but as I said earlier, all our answers should be written in 2 significant figures. So what exactly is 2 significant figures? Right, significant figures are basically any non-zero number, okay? For this, right, it is the non-zero number. So basically this number 2 here is our first significant figure, 6 is our second significant figure, this 0 is our third, 4 is our 4, and the 0 here is our 5. Okay, so we only want to have 2 significant figures here. So let's take a look at the first 2 significant figures, 1, 2. All right. The third significant figure is what determines whether we round up or round down. Okay. So any number that is from 0 to 5, we round downward. 0 to 4, we round downwards. And when it is 5 to 9, we round upwards. And the next, basically, when we round upwards, we add 1 to the second significant figure over here. So as you see here, this is 0, right? Okay, 3 is 0, and basically the third significant figure here is 0, which is smaller than 5, right? So we round downwards. So this is what we get, 26,000, okay, meters, because this whole graph is in meters per second, okay? And of course, every time we round it downwards, we must write 2 significant figures like this in our workings, okay? Once that is done, we can just write it down over here. Distance is 2,600 meters, okay? 2,600, sorry, not 2,600, 26,000 meters. Oh my goodness, I can't English today. So yes, 26,000 meters, all right? Please remember to write down your units properly. Okay? So for this question, this part over here, right? How do you get your full 3 marks? So, all right, this is a 3-mark question. So first thing, we need to understand that the first mark is given when your distance traveled is the area under the graph. That gives you your first mark, okay? Your second mark, right, is given over here, which is, give me a second. All right, your second mark should be given over here, which is you get the correct answer, 26,000 meters. This is your second mark. All right, and your third mark should be the correct numbers put into the equation. Third mark here. All right, so once you get all these three parts correct, you should get your full 3 marks for this question. Okay? Okay, so far, right? Fantastic. So let's move on to part 4. All right. So on a different day, the train takes 650 seconds to travel between stations A and stations B. So suggest one change to the motion of the train that leads to this longer journey time. So from stations A and B, we do know that the distance is 26,000 meters. All right. So it was stated that the train takes longer is equals to 6,000 seconds, right? The other time we saw before was, the time we saw previously, it was 530, right? So previously, it was 530 seconds, okay? So now the time is 650 seconds. So what happened? The most obvious answer for this is basically the train. Okay, the train traveled at a lower top speed. All right, so the train travel at a lower top speed. So because it has a lower speed, it takes more time to travel the same distance, right? So let's write that down. All right, the train traveled at a lower top speed. Okay, that's one very valid reason. So other valid reasons include maybe slower acceleration, lower deceleration, lower max speed. Any of these will get you your full 1 marks for this question. And with that, we are done with question number 1. Pretty simple, right? Okay. So once again, if you have any questions, I will come in to check in with you guys in chat later. If any questions for our teachers, please feel free to comment in the chat session, okay? Right, let's move on to question number 2. Okay, so for question number 2, we do see here that a resultant force is applied to an object moving with a velocity v in a straight line. So an object, right, is moving at a straight line v, and then, all right, and a resultant force is applied to an object. Okay, state 2 changes to the motion that the resultant force may cause. Okay, so what does a force do to an object? Okay, a force can change the direction of an object. The force can change the speed of an object. Usually that's most of the things that the force can do, right, to an object that's moving. Of course, if a force is moving this direction and then the force goes this direction, the object can move this direction. It changes its direction, all right? Okay, and because it changes its direction, it can also change the speed or velocity, something like that, all right? So let's write down our 2 main changes. So the first thing is the object. Object, okay, changes, okay. I should not have written that. I should have written this instead. State 2 different changes to the motion that resultant for object, to the resultant force may cause, right? So the first thing that may change is the direction of motion. So the direction of the object where it moves changes. And number 2, the speed of the object. Okay, the speed of the object changes as well. But of course, there's more than these two, answers. You can also say the velocity changes, the acceleration changes, so on and so forth. So these two, once you get these two parts correct, you should get your full 2 marks for this part. Okay. So state one other way that forces may change a stationary object. All right. So a stationary object, of course, when you exert a force onto it, it can accelerate, it can also change in shape and size. Okay, because if let's say you take a piece of sponge, as you see over here, you exert a force into it, don't you see the change in shape, right? So let's write that down. All right, so a force can change shape, change the shape of an object at rest. Okay, there we go. Okay, so with that done, next mark done. Okay, so let's go on to part B. Part B wants you to describe how a uniform meter rule, a pivot, and a selection of methods can be used to demonstrate that there is no resultant moment on an object in equilibrium. Of course, we can use a label diagram in our answer. All right. So this is basically planning an experiment similar to what we do on paper 6, but this is a lot more simple. All right. So they want you to use a uniform meter rule on a pivot like this. So do pardon the really unfortunate drawing that I'm doing over here. Okay, so this is the pivot and this is our ruler. Okay, all right, we have a ruler over here. Fantastic. This is not as bad, and we can use a selection of methods to demonstrate that there's no resultant moment of one object equilibrium. All right, so firstly, we can place the ruler directly in the center of mass, which is usually about the 50 cm mark, right? Okay, and then to the left of the ruler, we add, let's say, 50 grams over here. We add a 50-gram mass right down here, 30 cm away from the left side. Okay, at the left side over here, 30 cm away from the center. Okay, and then on the right side, we add, let's say, another different mass, maybe a bit more heavy, and it will be in a different, say, distance away. All right. Okay, now we take the moment of force on both sides, okay, which is moment of force is simply force, basically this multiplied force exerted by the mass, which is this mass over here, multiplied by the distance, perpendicular distance to the pivot, which is d. Okay, so we need to make sure that, right, the moment that's acting this direction, which is anti-clockwise, is equal to the moments acting clockwise over here. Okay, clockwise is equal to anti-clockwise, right? So let's write that down in our answer. All right. Firstly, okay, as you see, we place the ruler on the pivot directly on the center of mass because I want to get rid of the force acted by the ruler. Okay, so the ruler doesn't matter. And then we add a mass of 50 grams exactly 30 cm away from the pivot on the left side. All right, that's our first part. All right, on the right side, okay, what we do is we add a different mass to balance the whole ruler, and then we will measure the distance from the center of the ruler. And then, finally, we take the moment of the force, right, on both sides by multiplying the force and perpendicular distance, okay, from the pivot. Of course, please remember, right, this is mass, okay? So instead we should be calling this weight, right? Yeah, so we add a weight for, let's say, 5 newtons. Okay, right? Or should I say, no, should not be 5 newtons. We just add the mass first, and then we multiply mass by 9.8 to get a certain force, basically the weight of the mass, okay? And this is weight 2, different mass, okay? Yeah. Right, so we find the force, the weight actually, multiplying the weight and perpendicular distance from the pivot, which is our third part. And finally, we need to make sure, right, that the sum of clockwise moment is equal to the sum of anti-clockwise moments. The whole system is then in equilibrium, okay? Right, because when the sum of clockwise moment, as you calculate over here, is equal to the sum of anti-clockwise moment, and the two sides are balanced and not moving, this is the proof to show, right, that an object that a system in equilibrium, right, should not have a resultant moment, no resultant moment, all right? And that's how you solve this question. This is a bit more convoluted and a bit more difficult to write. But if you, right, if you draw this diagram and you mention that the meter rule is sitting on the pivot right in the center, this gives you your first mark, okay? Right, so your second mark is given if you mention that you add mass on one side and then add another mass on the other side to balance the ruler. This gives you your second mark, all right? The second mark is here. The third mark is given when, right, you find the moment of the force, which is multiplying the force and perpendicular distance to the pivot. That gives you your third mark. And finally, right, your fourth mark is given when you write, right, the sum of clockwise moment is equal to the sum of anti-clockwise moments when the system is in equilibrium. That gives you your final fourth mark, right? And that gives you your full 4 marks for this question. Okay. So, if everyone's clear, yeah. If not, once again, please feel free to answer to comment in chat, comment in our live chat. Our teacher, Mr. Narayan sir, is over there right now. He will look through your questions and we will take a look at it and explain to you if you have any questions or any queries regarding this question. All right. So far, no questions in chat. In that case, let's move on with our paper. Okay, 1 second. Okay, thank you, Narayan sir. Now I know that there's no questions right now. Let's move on to question number 3. Okay, question number 3 of this paper. Okie dokie. So question 3 shows figure 3.1 and it shows the side of a concrete track on a skateboard park. Okay, so you should have probably this dude right here doing his skateboardy stuff, right? All right, and he usually goes from A to B or C. All right, so a skateboarder initially is at rest at point A. So let's say she was here, okay? And then she travels from point B through point B and then comes to rest at point C. So we are to describe the transfer of energy the skateboarder travels from A to B to C along the concrete track. So first thing first, as you can see, when the skateboarder is at point A, right? A is taller than B. So A has a height difference over here, and thus when the skateboarder is at point A, she should have gravitational potential energy, right? And when the skater starts off at A and then rolls to B, right, the gravitational potential energy is converted into kinetic energy, right? Okay, and from B to C, right? Excuse me. From B to C, the height changes again. Now the height goes upwards. So at C, right, the skater should have gravitational potential energy again. So it converts back to GPE. But at the same time, if you notice, right, C is lower than A because some of the energy at A is not just converted to KE, but is also converted elsewhere to heat energy, sound energy, and so on and so forth. So some energy is so-called lost to the surroundings in this matter, right? So let's answer this question, okay? So let's write down our first part, right? First point, from A to B, right? The skateboarder's gravitational potential energy is converted into kinetic energy, right? That's the first part, right? And let's move on. Let's go to the second part as well. Okay. Right. So from B to C, her kinetic energy is converted into gravitational potential energy. All right. And then, of course, we did mention that during this whole process, right, some of this gravitational energy, potential energy, and kinetic energy is converted into, heat and sound energy. So yeah, some of the gravitational and kinetic energy is converted into heat and sound energy, right? So once you have written, right, that there's a conversion from GPE to KE and back to GPE again, that gives you your first mark. Okay, that gives you your your first mark over here. And then during this whole process, some of this energy, this GPE and KE, is converted into heat and sound energy, or is lost to the surroundings, gets you your second mark. That's how you get your full 2 marks for this question. Okay? All right. So pretty straightforward, yeah? Okay, energy conversion. Now let's go to part B, part 1, all right? So as you can see here, B is at ground level and C is 2.8 meters above the ground level. The mass of the skateboarder is 65 kilograms. All right. Now we have to calculate the work done on the skateboarder as she travels from B to C. All right. So they want to find the work done. W, all right. Work done is equals to energy required to do the work, and the work is basically moving the skateboarder, which has a mass of 65 kilograms, up to C. So this work done is equals to the change in gravitational potential energy, right? So the work done is equals to mass, which is 65 kilograms, multiplied by the gravitational constant, 9.8, and multiplied by the height. The height is 2.8 meters above ground level, right? So let's write that down. Let's do the maths in our calculator. We should get this number, 1783.6. All right. And of course, we want to round this to 2 significant figures. So let's take a look at our third significant figure. It's 8. 8 is greater than 5. So we round 7 upwards. And thus, we get 1800 joules, which is in 2 significant figures. All right. So, of course, over here, please make sure to write your units properly, right? Joules is the unit for work done, or should I say the unit for energy as well, okay? Right, so if you write down this equation, right, and wrote down the correct numbers over here, you get your first mark, okay? And if you get this answer correct, this is your second mark. And that's how you get your full 2 marks for this part of the question, okay? Right, let's move on to B part 2, all right? The skateboarder falls off at B and she hits the track and comes to rest after a few milliseconds. So poor girl, he fell off the skateboard and well came to rest after a few milliseconds, right? So we have to state the equation that defines the force F with which the skateboarder hits the track and state the meaning of any symbols we use. Okay. So over here, we are given, right, that the skateboarder falls off the skateboard at B and she hits the track and comes to rest after a few milliseconds. Okay, this is the clue we have over here. So we are to state the equation that defines force F. Okay, all right, and time t. So the two important variables we have over here are F, which is the force, and t, which is the time taken in a few milliseconds, right? So the only equation that ties everything together is pretty much force is equals to change in momentum divided by change in time, right? If you all remember this equation, our famous F equals to ma, right? All right, okay. Now, let's take a look here. What exactly is P? P is momentum, right? Momentum is mass times velocity, all right? So, if we put this into here, force is equals to change in momentum divided by change in time, right? So, you take V over T, right? Delta V over delta T multiplied, which is also equals to m times a. So pretty much it's just another application of Newton's second law, isn't it? F equals to m times a, right? So the equation we should use over here is, okay, let's write it down. Okay, use here is F is equals to delta P, change in P over change in T. Okay? Okay. So delta P is the change in momentum. All right. Okay. And okay, which is change in velocity, right, multiplied by mass. Okay, by the mass of the object, which is the skater, right? And delta t is the change in time. Okay? All right, so this question is not that easy to work out of, but if you manage to, number one, right, if you write down F is equals to delta P over delta T, right, and basically if you also mention that delta P is the change in momentum and delta T is the change in time, you get your first mark, okay? All right. So once you write that down, and also everything over here, you should get your full 2 marks, okay? All right, so 1 mark even if you write down this equation, and your second mark is when you explain what is delta P and what is delta T, okay? Right, so pretty much that's it, okay? Right, is everybody clear so far? All right, very good. Okay, so question 3 done. Let me take a look at chat whether there's any queries. Okay, so all right, so hi Louis, Polycarp, right? So when I write an answer without rounding to two significant figures, will it be wrong? Well, the thing is, it's not wrong, but the thing is, you won't get your full marks because it is a Cambridge necessity to round everything to two or three significant figures. So to make things easier for you and to make sure you actually get your full marks, please round everything to two or three significant figures. In my case, I use two significant figures, okay? I hope that clarifies the answer for you, all right? Thank you for sending in the query, Louis. And with that, let's move on to question number 4. Okay, so question number 4, right? It shows a heater that used to warm the air in the room, okay? And we are to state the main method of thermal energy transfer throughout the air in the room. Now, this is a very straightforward question. As you know, a heater, right? A heater works via convection, okay? So what that means is the air goes into the heater, right? The cold air goes into the heater, it gets heated up, all right? And then the hot air rises, okay? And moves around the room like that, okay? So this way of heat transfer is called convection. And writing convection gives you your full 1 mark. Easiest 1 mark in the universe, right? Okay, so A part 2, right? They want you to answer how the heater warms all the air in the room. I mean, I just explained it, doesn't it? So, 1, as I said before, the cold air goes into the heater, right? And gets warmed. And the warm air escapes the heater and moves upwards and into around the room. So that means the cold air goes in to replace the hot air. And the cycle continues like that, okay? So let's write down this in nice English, okay? At least this will be readable. All right. So our first mark, we need to say that, right? The heater hits the air around it, all right? And the warm air, right, rises as it's less dense than cool air, right? Of course, when air is hotter, it rises. When air is cooler, it sinks, right? Standard stuff, right? All right. Then we need to write that the cool air then replaces the warm air, while the warm air circulates the room via a convection current. Okay? Okay? And then that's it. Pretty much that is how you get your full 3 marks. But you might ask, Mr. Zong Yang, how you get 3 marks from this question? Well, I will give you the answer right now. So 1 mark awarded if you write warm air rises and cold air sinks, right? Okay? Warm air rises as it's less dense, right? That's the first mark. Okay? The second mark is if you, okay, warm air rises, okay? First mark is warm air rises. Second mark is given if you say, right, the warm air is less dense than cool air. That's your second mark, okay? And your third mark is when you write, right, the cold air replaces the warm air, and then the warm air moves around the room via a convection current. By writing this, you get to your third mark. This is how you get full 3 marks for this question. Okay? All clear, yeah? Okay, so that is how you get your 3 marks for this. Okay? Now, let's move on to part B. Calculations. Give me a second, some water. Okay, so part B. The power of the heater is 2.0 kilowatts when it's connected with a main supply of an EMF of 230 volts. Okay? And for part 1, we are to show, right, the current in the heater is approximately 8.7 amperes. So the answer is already given to you. We just need to prove that it is 8.7 amperes. Okay, so 2 kilowatts, 230 volts. Okay, so first things first, we kind of know that, for power, electrical power is equals to, right, voltage or EMF multiplied by the current. Okay, so what we do is, let's rearrange this for a while. We multiply RA on both sides. We divide voltage on both sides. So current is equals to, all right, power divided by voltage. Okay, so the power of the heater is 2.0 kilowatts. So let's convert it to normal watts. This should be 2000 watts, right? 2 kilowatts is 1 kilowatt is 1000 volts, right? So 2000 watts divided by EMF for 230 volts. Okay, and that should get you, okay, 8.695, yada yada yada. And of course, over here you see, right? Over here, we want to convert this into two significant figures because our answer over here asks you for two significant figures. Okay, so 8.6. This is the first, this is the second. We look at this, okay, the third number. Oops. All right. We take the third number. Now let's take a look at it. 9 is greater than 5, of course. So that means we round up the number. So 6 will become 7, right? And that gets you 8.7 amperes in two significant figures. All right. So I hope this actually brings some some answers to your query, especially Mr. Lewis, who asked, why is it possible? Is it will you be penalized if you don't update, if you don't write your answers in two single figures? Yes, this is actually very important. But do take note, right? You will only do this, right? This rounding up or rounding down, right? Only when you are to present your answers. Okay? Right, so with that, if you, number one, write down P equals to V times I, that gets you your first mark. Okay? And if you write down the numbers correctly like this, 2000 divided by 2300, that gives you your second mark to give you your full 2 marks for this question. Okay? Right, let's move on to part number 2. All right, so the plug over here, right, the plug connecting the heater to the main supply is fitted with a fuse. And the fuse ratings of 3, 5, 10, and 13 amperes are available. So state which fuse is used and explain your answer. So what exactly is a fuse, right? A fuse is pretty much an electrical device, right, like this. You connect it to some to a wire, to a system, right? And inside here there's a thin wire, and this thin wire will melt and break the circuit, all right, if the current of the circuit go beyond a certain current. For example, 3 amperes. If this fuse, right, detects, not say detects, but it has a current of 3 amperes passing through it, the thin wire inside here will melt and break the circuit. All right, so over here you can see, right, the current to heater is 8.7 amperes, right? It takes this much amperage to run this heater. All right, so that means if you have a 3 ampere and a 5 ampere fuse, right, even before the heater can run at full capacity, the fuse inside melted already, means it doesn't work. So 3 and 5 are out. 10 and 13 are usable. Okay, right? But here's the thing, right? If you want to use the 13 ampere fuse, it is still possible, but there's a chance, right, that if a current that goes beyond 10 amperes, right, it can damage your heater. So to be very safe, we use the 10 amperes. All right, let's use the 10 ampere fuse. Okay, right, so why do we use the 10 ampere fuse? Okay, so because the heater okay, operates at 8.7 amperes, okay? So a 10 ampere fuse allow current to flow, okay? If it is below 10 amperes, but cuts the circuit, okay? If it is beyond 10 amperes, okay? Right. So pretty much if you write down any either 10 or 13 amperes, you get your 1 mark. And you need to explain, right? 1 mark is you're given if, right, if you write any of this down. So if you use a smaller fuse, right, the smaller fuse will melt for the normal use of heater. The smaller fuse stops the heater from working well. A larger fuse allows too much current without melting. A larger fuse may not melt if circuit is damaged. The fuse rating must be higher than the normal circuit, or the fuse melts if the current is too high. Any of this will get you your next mark over here to get you your full 2 marks. Okay? Right, I hope this question is well explained. And with that said and done, okay, let's move on to question number 5. All right. So I hope I answered some questions well, and especially to Mr. Lewis who asked on the significant figures. I hope that answers your query as well. That clarifies your query. Okay. Right. Now let's move on to question number 5. Okay. So here, a ray of light is incident on the soap film, and here it shows a magnified image on a small part of the soap film. A ray of light is refracted as it enters the soap film. Okay, so the refractive index of the soap film is 1.28. So we are to define the refractive index in terms of speed of light. All right. Okay, if you do remember, right, the refractive index n, right, is equal to the sine of actually no, n is equal to the ratio of, right, when the speed of light in the medium, okay, in medium, divide the speed of light in vacuum or air, okay, and this n here is a ratio, so let's write that down. Okay, so we do know that this n, number n, right, is the speed of light in the soap film, right, divided by the speed of light this time round in air. Okay, let's write that down. The refractive index, okay, of a medium, right, is defined, right, as the speed of light, okay, in air. Oh, yes. I'll say I'm so sorry. This is my mistake. Speed of light in air divided by speed of light in the substance. Okay, sorry about that. This is n is basically the refractive index is basically the speed of light in air divided by speed of light in the substance, or in this case, the soap film, right? So let's write that down. So it's defined as speed of light in air, all right, divided by speed of light in the soap film. Okay? And once you write that, you should get your full 1 mark. Okay? All right. So let's move on to part B. Okay? So that we are to show that the angle of refraction as the light enters the soap film is approximately 43 degrees, right? So first, let's find the incident angle, okay? As you see over here, this is not the incident angle, but instead we have to draw the medium like this. Okay, we have to draw the medium. Sorry, not medium. Yeah, we have to draw the medium. This is the normal. Yes, this is normal. Okay. This is not the angle of incidence. This instead is the angle of incidence. And this angle is equals to 90 degrees, okay, minus 30, which get you 60 degrees over here. So the incident angle is 60 degrees. So let's do this. You don't know. N is equals to sine I divided by sine R. I is the angle of incidence, R is the angle of refraction. Okay, so we do know that N is equals to 1.28. Okay, sine I is equals to sine 60, which is our angle of incidence, divided by sine R, which is the angle of refraction. So let's do a little bit of manipulation. Move sine I over there. We multiply both sides by sine R, and we divide both sides by 1.28. So we get sine R is equals to sine 60 divided by 1.28. Okay, and we do this. R is equals to sine inverse sine 60, all right, divided by 1.28. Now let's plug this into the calculator. And once that's done, you should get 42.5777, so on. And of course, as you see over here, this is in two significant figures. So let's round this up to two significant figures. 5 is equal to or greater than 5, so we round 2 to 3. You round it upwards. 43 degrees in two significant figures. Okay? And that is how you get your full 2 marks. Your first mark is when you write down the incident angle is 60. All right, over here. So incident angle is equals to 90 minus 30 degrees, which will equals to 60 degrees. Sorry, I should have written this just now. So this is your first mark, okay? And then your second mark is given when you write this equation, n is equals to sine I over sine R, which is your second mark over here. By doing that, you should get your full 2 marks, okay? And next, we need to use something that's a bit, wait a second, where did I put my protractor? Okay, I didn't have a protractor with me, but I have already done the drawings beforehand. Okay, where's my protractor? I don't have it with me. Polly. All right, so not to worry, let's continue with this. So on figure 5.1, carefully draw the refracted ray in the soap film and label the angle of refraction. Okay, so as you can see over here, 60 is here. So usually in here, right, in this this area which has a denser, optically denser, right, the incident air, the incident ray, right, the angle should be greater than the refracted angle. So please put your protractor over here like this, okay, and then measure like that, 43 degrees, okay. Now once that's done, you should get something like this. All right, if you are still not very sure how this is done, you can consult my the solved paper, which um I will be posting in our website, CIE past papers, right? So this is 43 degrees, like that. Okay. So just to take note, right? This is not accurate. Please use a protractor for yourself. Don't be like me. I do this because I cannot measure angles on my computer screen right now. So this is what we will do. Okay. So that's that. And once that's done, okay, your 2 marks is given if you, for number 1, you draw the normal. This is the normal, by the way. Okay. You draw this correctly. It's 9 degrees. Okay. Please use a protractor for this as well. And 1 mark drawn, 1 mark also awarded if, right, your refracted ray drawn over here is correct and the angle of refraction, which is 43 degrees, is labeled. So once that's done, you should be able to get your full 2 marks. Okay? Pretty straightforward, yeah? And now let's go to part C. C is very straightforward. The ray of light is monochromatic. Okay, monochromatic is the key. Red light, and if a wavelength of 680 nanometers in air. So what exactly is monochromatic? This is very, very straightforward. Mono means single, chromatic means color. So, and in science term, it means a light of a single frequency or a single color, right, in English. So let's write that down. A monochromatic, right, light is a light ray of a single frequency. Right? Just writing like that. 1 mark. Done. Okay? Now, let's move on to part 2. We are to calculate the frequency of light. Okay? Yeah, so the frequency of light is very straightforward. We do have this equation. If you please remember this is very important. V is equals to F lambda. Okay? V is the velocity, the speed of light. F is the frequency, and lambda is the wavelength. Let's calculate the frequency. So F is our main player here. We move lambda over the other side by dividing both sides. F is equals to V over lambda. Excuse me. Now, as you know, speed of light is very easy. It's 3.0 times 10 to the power of 8 meter per second, right? Divided by the wavelength. We are given that wavelength is 680 nanometers. Nanometers is, right, 10 to the power of 9 meters. So it's 680 times 10 to the power of minus 9. Okay, this is our working. Let's plug this into a calculator and you should get, okay, 4.4117 yada 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 times 10 to the power of 14 hertz, right? Hertz is the unit for frequency, okay? And of course, let's round this to 2 significant figures. Now, significant figure 1, significant figure 2, significant figure 3. Now, 1 is the third figure, and 1 is smaller than 5, so we round down. So we remove everything else at the back. We should get 4.4 times 10 to the power of 14 hertz. Okay? And that in 2 significant figures, right? So the answer is 4.4 times 10 to the power of 14 hertz. And that gets you your full 3 marks. So first mark, we do need to know that the speed of light in air is 3.3 times 10 to the power 8. That is your first mark. All right. Second mark is if you write down V equals to F lambda. Second mark. Third mark is getting the correct answer. And that gets you your full 3 marks over here. So far so good, right? Okay. Let's move on to question 6. And let me take a look if there's any questions or any queries from chat. So, all right, Luis, thank you so much for sending the question. I hope this, helped you greatly. And thanks for Narayan sir for also explaining in the comment section in the chat. All right, thank you so much. Let's move on to question number 6. Oops. All right, thank you, Narayan sir. No other questions. Let's move on to let's start with question 6. All right, so question 6, we show a person using a magnetic window cleaner, and the part outside of the window is attracted to the inside part of the glass window, and it looks something like this. All right, each part of the window cleaner contains 2 magnets, and it's shown in 6.2, the magnetic field between the parts of the window cleaner. So as you can see, the handle is here for you to hold on to it, and then when you move it around on the window, the other part will also move around with you. So you just need to attach a piece of cloth underneath, and then the cloth outside will do the cleaning of the window, right? Pretty smart, yeah? So let's move on to part A. So glass is not a magnetic material. Well, of course, Captain Obvious, glass is not, right? So we are to state the difference between magnetic and non-magnetic materials. Well, the most Captain Obvious answer to say is that non-magnetic materials are not attracted by magnets, right? So that actually does give you your first mark already. So of course, magnetic materials are attracted to magnets. Non-magnetic materials are not attracted to magnets. Very, very simple, yeah? Magnetic materials, right, are attracted to can be attracted to magnets. Okay? While non-magnetic materials, right, cannot. And just like that, right, 1 mark. All right. So there are actually a few more options for this. For example, magnetic materials experience a force in magnetic fields, and non-magnetic materials don't experience a force in the magnetic field, right? So this is another answer for that. So as long as you write either of these answers, you should get your full 1 mark. Okay. Right, so now let's move to part B. So part B wants you to suggest a suitable material for magnets in the window cleaner, and we are to explain our answer. So what are the magnetic materials we do know is steel, is iron, is nickel, and I can't remember the last one, but basically most magnets that we know today, permanent magnets, right, are made up of steel, because steel don't lose its magnetism easily, right? So let's write that down. Right, so the magnet should be made from steel. Right, should be made with steel. Okay, right, this is because steel, right, does not lose magnetism easily, right? So, or you can just also write if this is not your thing, because steel creates a good permanent magnet, right? Or steel does not lose magnetism easily. Writing down why it should be a steel and a good reason why just gives you your full 1 mark. Okay, right? 1 mark awarded if steel is given. Okay. Now let's move on to part C. Part C wants you to label the poles of the magnets in 6.2. All right, let's take a look at 6.2. We are to label all the poles of all these magnets. Okay, so pretty much, right, the first thing you need to know is for a magnet, right? If you take a look at the magnetic field, okay, if the magnetic field moves away from this pole, right? This pole should be a north pole. Same thing here. As you can see, this is also the magnetic field lines are pointed away from this pole. It should be the north. And of course, the north attracts to the south. So when all these magnetic field lines point to this pole, it should be the south pole and vice versa. Now, of course, you cannot have two of the same poles within the same magnet. So this should be the north pole, and vice versa over here. This should be the south pole and south pole. Okay? Now, if you write all of these properly, you should get your full 1 mark for this question. Okay? 1 mark. Done. Now, part D. Okay, state how the field lines in 6.2 shows different strengths of the magnetic field between the magnets. So, how does the field line show different strengths of magnetic field, right? So if you do notice, right, when a magnet, north and south, right, when they are brought together, right, you have like say one line here, you have a second line doing this. Oops, it should go here, it should go here, and then it should go here, right? And so on and so forth, right? So as you go closer to this, right, if you notice, the space between these magnetic field lines are closer together, right? And as you move if you move further away like this, right, the magnetic field lines are further away from each other. This means, right, at these places, right, the magnetic field is not as strong. And when these lines are closer to each other, right, the magnetic field is stronger. All right. So the correlation over here is also very straightforward, right? The closer the magnetic field lines, okay, are together, all right, the stronger the magnetic field. Right, so the closer the magnetic field lines are there together, the stronger the magnetic field. Straightforward, 1 mark, okay? Very easy, yeah? This is a 4-mark question. Magnetism is pretty much the easiest topic of IGCSEs, right? This is pretty much everything you learn in elementary school, okay? All right, so let's move on to question number 7. Okay, so question number 7. Let's take a look at this, right? So figure 7.1 shows a sketch of a current voltage graph of a certain electrical component, and we are to name this electrical component and explain how you identify the component from the graph in 7.1. So as you can see here, when voltage increases, current increases exponentially, but increases exponentially at first and then it increases normally, right? It becomes a straight line afterwards. But when voltage is negative, right? This is negative voltage, right? Current does not go downwards. So pretty much in a normal, in a normal ohmic component, right? Okay, this is usually the graph. Okay, this is current and this is voltage. Usually this is what happens. Okay, but in this case, current only flows when voltage is positive, and it does not flow when the voltage is negative. So we kind of have something that only allows current to flow in one direction, and there's only 1 to 2 components that does. There are only 2 components that does that, right? The 2 components are either the LDR. Is the LED, light emitting diode, right? Which is this thing, right? This thing, I think that's how you draw it, right? Yeah. And of course, we have to know there's also the diode, which looks something like this, right? So we just say it's a diode. Pretty straightforward. Okay. So this item, this component over here is called the diode. Okay. And the diode only allows current to flow in one direction when voltage is increased. Let's write that down. The current only flows in one direction, okay, when voltage is increased. Okay, yeah, all right, so 1 mark for the correct component, which is the diode, and 1 mark for the correct explanation like this, okay? And now we are to draw a circuit symbol for this component. How does the diode look like, right? So first let's draw the, let's draw the line out here. This is our cable, right? This is our electrical line. And we should draw first a triangle. Okay, I think I should draw this nicer. Okay, let's draw a triangle pointing to the right, like this. Okay, and another line like this. Okay, this will get you your full 1 mark. Okay, this is the circuit symbol of a diode. All right. Okay, very straightforward so far. You should get your 3 marks from part 1 and part 2 of 7A. Okay. Now for 7B, let's take a look at this equation, this circuit over here, not equation, this circuit over here. All right, so in this circuit over here, figure 7.2 shows an electric circuit for two identical electric heaters A and B connected to a main supply of 230 volts over here. Okay, so S1 is closed and S2 is open. So for our first part, right, S1 is closed. Okay, switch 1 is closed. All right, and the reading on the ammeter is 3.9 amperes. All right, so let's ignore this part over here, right? And we get a reading of 3.9 amperes when S switch 1 is open, which means the circuit over here, right, has a current reading of 3.9 amperes. So let's calculate the resistance of heater A. So we do know that V is equals to I times R. Okay, now we want to put R as our subject, so we divide I on both sides. R is equals to V over I. Okay, what's our value of V? V is 230 volts. Our value of I is 3.9 amperes, so it will be equals to 230 volts divided by 3.9 amperes, and that will give you an answer of 58.9743, yada yada yada. Of course, let's turn this into two significant figures. Let's take a look at the third figure. 9 is greater than 5, so we will want to round up this number, and which means 8 becomes 9, and thus we should get 59 no points. It should be just 59 and 59, right? It should be 59 ohms. Remember, the unit for resistance is ohms, okay? And let's write it to two significant figures, okay? Just like that, we should get your 2 marks. 59 ohms. Okay, so basically, your to get your first mark, right, you need to write down V equals to IR or R equals to V over I. That's your first mark. Second mark is the correct answer over here with the correct unit as well. Okay. Okay. Ooh, that. Okay. So now we have the reading of the current, the voltage, and also the resistance. Now we are to calculate the energy transferred by heater A in 5 minutes. Okay, so first things first, we know that energy is equals to the power of the appliance multiplied by the time used, right? Okay, so power, as we have done before, P is equals to, power is equals to voltage times current as well. So we can just use that as well. So equals to V times I, which is that multiplied by time. Okay, that's the first part. And now let's put in all the numbers one by one. Okay, so V is 230, I is 3.9. Okay, multiplied by time, 5 minutes. But it's 5 minutes. We want to bring everything down to seconds. So let's multiply it by 60 seconds. Okay. All right. So now let's plug everything in the calculator and let's calculate. And we should get this number, which is nice. Okay. Right. And then, of course, let's once again round this to two significant figures. 1, 2, 3, 1, 2, 3. 9 is greater than 5, so we round this upwards. We get 270,000. E is this in joules. Okay, so remember the unit for energy is in joules. Okay, two significant figures, right? So let's write that down. 270,000 joules. All right, so how do you get your full 3 marks for this question? Simple. First mark, when you get E equals to V times I times T, that's your first mark. Second mark, when you write, okay, when you decipher, right, 5 minutes is equal to 5 times 60 seconds, that's your second mark. And your third mark is for the correct answer, okay, to get your full 3 marks. Straightforward, yeah? Okay? Okay, so yes, of course, Louis, resistance has the units of ohms, okay, and we write it in the Greek letter omega. Oh, all right. Okay, let's move on with part 3. All right, so in part 3, switch 1 is closed, switch 2 is also closed. So we are to determine the reading on the ammeter and show your working. Yeah, all right, so over here, now we close switch 2. Okay, so A and B are now connected in parallel. So how does it look in our diagram? So this is our power supply of 230 volts. Okay, and we should draw every time when I need to deal with a parallel circuit. I usually would like to redraw the circuit because it makes a lot more sense to me this way. It depends on you, but for me, I like to do it this way. Okay, so this is our heater 1, this is our heater 2, and this is switch 2. Okay, and this is our ammeter. Okay, and this is our switch 1. Okay, now this is closed. Okay, this should be correct, like that. Okay, so this is our original graph. Okay, this is our original circuit. I usually like to turn my circuit into something a lot more so-called textbook parallel. It makes things a lot easier. Okay, yeah. And over here, we do know that this resistor has a resistance of 59 ohms. So let's write it down. 59 ohms. This is heater A. Okay, this is heater A. Heater B, we don't know yet. Okay. All right. So they are identical. I'm sorry. So heater B is identical to A. So which means this is also 59 ohms. Okay. Right. So we are to find this. So all right. So now that you know A and B are in parallel, let's find the total combined resistance. Okay, actually, we should not do that. Okay, there are actually two methods to do this. I'd like to show you the easy method, which is pretty much we don't really need to, we don't really want to do too many calculations. So let's do the easy method. The other method, I will tell you guys what it is, but let's take a look at the easy method first, okay? So we already do know that when only heater A is connected, right? It has a voltage. It has a current reading of 3.9, right? 3.9 amperes going here. Now, since there are now two identical heaters, right? So this current over here should also be 3.9 amperes. Okay? So as you can see, right? If you take 230 volts, you do the maths here, okay? This is V equals to IR, right? And then you do some manipulation, you find I over here is 3.9 amperes. And for this branch over here, this is also 230 volts, right? It's connected in parallel after all. Divide by 59 is 3.9 amperes on this side. So if you take these two 3.9 amperes, you combine them together and goes to the ammeter, you just need to add this and this. So pretty much, there we go. I total, right, should be equals to current in A plus current in B. As we do know, that is 3.9 plus 3.9, and that gives you 7.8 amperes. All right, so just like that, you get your, oh dear, you get your 2 marks. Easily like that, okay? The other more so-called convoluted method is as I said earlier, you can find the combined resistance of this, which includes doing this equation, which is a massive pain to try and resolve. Okay, so if you remember this equation, good for you. But let's do it this way, like this, and over R. Then you flip everything around and do the shenanigans. Yeah. Okay, R should be equals to multiply R on this side, and then you divide this by that side. You should get 59 over 2. Yeah. Right? So something like that. And afterwards, you just need to do the usual V equals to IR thing. Okay, so this is the second method. Okay, V is 230. Divide by R, which is 59 over 2. Right? And you should also get back the same answer, 7.8 amperes. I mean, you can do the math yourself. This is the same, okay? So this is method 2. Please try this out yourself. This is a very fun experiment to practice how to find combined resistances, okay? So it's a little bit more convoluted, a bit more tedious, but it still come up to the same answer. Try this out yourself, okay? All right, let's move on. Okay, question 8 now. Okay, so question 8, right? We see a part of a simple AC generator. All right, so remember, right? This is an AC generator. This is not a DC motor, okay? A lot of people mix these two up together, so take note, all right? In a DC motor, right? I think these are two different items, right? In an AC generator, right? A and B is very simple, right? The A are carbon brushes, all right? And B are slip rings. Okay. In a DC motor, you also have carbon brushes, but this instead of slip rings, they are split. Split ring combinator, right? So in a DC motor, they are split ring commutators, but in an AC, in an AC generator, they are slip rings. Okay, so these are the difference. So please take note. All right, these are two very different things. So even though they are very similar, they have a coil. They do spin. One generates electricity, the other one generates movement, but they are very different. So please, if you are not sure, please go ahead and watch our videos on the DC motor and the AC generator. If I'm still not wrong, there should be videos 4.22 and 4.23 and 4.25. I may be wrong. So once again, if you are very unsure and you have access to Homeschool.Asia or Homeschool.Asia or My Second Teacher, you can take a look at the videos, corresponding videos for IGCSE Physics, and they should be 4.22 and 4.24, right? I think so. Okay, let's move on. Okay, so let's move on to component C, right? Component C over here is made of soft iron. So we are to describe the effect of this component on the generator. Okay, so pretty much the soft iron there is only here for one reason only. It helps to strengthen the magnetic field of the magnet. So let's write that down. All right, so the soft iron core, as we say over here, right, helps to strengthen, okay, the magnetic field all right, of the magnet. And just like that, 1 mark, done. Okay, straightforward. As long as you write down that it strengthens the magnetic field of the magnet, you should get your 1 mark. Okay, and sorry for the missed out for the previous part. All right, if you write carbon brushes, that's 1 mark. Slip rings, second mark to get your full 2 marks for this part as well. Okay, let's move on to part B. So this the coil of the generator, all right, okay, rotates at a constant speed of 2 complete revolutions per second. Please remember, right? 2 complete revolutions per second. Oops. 2 complete revolutions per second. Yes, pardon my Singlish coming through. Okay, so we are to sketch the graph of EMF generated against time on the axis in figure 8.2. And second thing to take note, I myself even missed this as well. All right, the coil is in the position shown in 8.1 at time equals 0. Okay, so please take note of this, right? The coil starting position is very important, and basically it's shown over here like this, in this position right here. Okay, it looks like this right now at position 0, and it spins twice, right? It makes 2 complete cycles, okay, in 1 second. So as you can see, right, the magnetic field is moving like this, okay, and then okay, let's say this is, they didn't say it's north or south, but the magnetic field is directly pointing downwards. So when you spin this coil over here, right, the coil cuts directly into the magnetic field at 90-degree angle. So at this point of time, right, when t equals to 0, okay, the EMF generated is maximum. Okay, so do take note, EMF at t equals to 0 is maximum. So we need to draw a graph, right? A graph to show what is EMF like against time. Usually for an AC generator, of course, it's an AC alternating current. The graph looks like a sine or cosine graph. This time around, because EMF is maximum at t equals to 0, let's start over here. Okay, this is the maximum. Okay, it starts over here. Now, you also need to know, right, it completes 2 complete revolutions per second. So this is a graph in 1 second, so it should have 2 complete cycles in 1 second. So so basically this whole thing, right, it completes a cycle here in 0.5 and here in 1.0. So 1 complete cycle, 2 complete cycles. Okay, so this is pretty much a cosine graph. So let's draw the cosine graph, and basically we can start doing this. Okay, so since this is maximum here, it should go minimum here, and it goes maximum there, minimum there. Okay, so these are the points. And then of course it should hit 0 right in the center, like this, like this, like this, like this. So let's try to draw a cosine graph as accurately as we can. Okay, so this should be straight down, then this should be like this. Okay, and this should be going back up. Okay, and this should be going back down again. And last but not least, one more time. All right, so remember this is a cosine graph. Unfortunately, my drawing is not the most pleasing to the eye and not the most accurate, but please draw with a pencil if you are doing so. Okay, if you make sure, right, all these, I'm sorry, excuse me, all these lines, right, it has to be as smooth as possible. It should be nice and curved, nice and smooth, not like mine, like I don't know, an orange, skin of an orange, very bumpy. You should not be like that. It should be nice and smooth. Okay. And when you're drawing this, please draw with a pencil. So if you make a mistake, you can you can use an eraser to remove your mistakes easier. Okay. Okay. So this part is worth 3 marks. So how do you get your full 3 marks? Okay. So first mark is given if your graph looks sinusoidal, which is, I mean, cosine and sine are sinusoidal, so that's your first mark. Second mark is if you put 1 cycle, which is from here, from one maximum to the next maximum, it is 0.5 seconds. This is your second mark. Okay, and the third mark is if your minimum and maximum is at 0. Okay, right. So basically, in the third mark is if you start at maximum at 0, okay, and return to maximum in 0.5 and 1.0. Okay. The other option is to draw the graph starting from here. It works as well. So basically, if you draw from down here, it should, it should look a bit like this. If you are drawing the graph from a different side, right? So if you start from minimum, you should have two other minimums as well. Okay, so pretty much that's how you get your full 3 marks. Okay, let's move on to part C. Okay, part C, let's try and answer this. Yeah, so in power stations, transformers are used to step up the voltage of electricity generated before it is transmitted through cables over long distances. Right, so we have transformers now. Okay, so we are to explain the advantages of transmitting electricity in high voltages. Okay, so why do we transfer electricity in high voltages? Why is this advantageous for us, right? So basically, once again, let's talk about the power, right? P is equals to I square R, right? R being the resistance of the wire that you're transmitting across, and I that regarded is the current, right, of the the current of the electricity that's transferring through the wire. Okay, so if your current is very, very low, right, basically you have also this thing where if in a transformer, if your current is high, your voltage is high, your current is low, and vice versa. If your voltage is low, your current is high, right? So if your current is low, right, I squared times R, which R is constant because the resistance across the whole thing, across the whole system, the wires that you are transmitting the electricity across, right, is constant, right? If your current is low, right, the power that is lost through this wire will be low. But if your current is high, your power loss will also be high, no matter what. So it is advantageous for high voltage and low currents. Okay, let's write that down. Right, so let me just do this and do this. All right, so okay, at high voltages, right, the current is lowered to reduce power loss. And okay, it is because of this equation P equals to I square R. Let me just write this as okay. Excuse me. Wow. Okay. So basically that's it, really. So because, right, of this equation P equals to I square R, okay, having a lower current, right, reduces power loss via the cables. And that's the reason why we use, higher voltages. And of course, having a high voltage and low current means you can use cheaper cables, you can use thinner cables, and these are also two other answers that are acceptable. So having this, basically at high voltages, current is lowered. That's your first mark. And lower current reduces power loss by cables is your second mark. And that's how you get your full 2 marks for this part of the question. All right. Okay, so now let's move on to C part 2, which is where a power station generates electricity at 25,000 volts, okay? And the transformer steps up the voltage to 300,000 volts. The primary coil of the step-up transformer has 450 turns. Let's put down each value properly, all right? So, number of turns in the primary coil is 450 turns, right? And then the voltage in the primary is 25000. The voltage in the secondary is 300000 volts. All right, so as you know, the transformer equation looks like this. Number of coils in the primary divided by number of coils in the secondary is equals to the voltage in the primary divided by voltage in the secondary. Okay, now let's arrange this thing so that your number of turns in the secondary is the subject of this equation. So multiply both sides by this, we should get an S should be equals to and P, right? Okay, whoops, I should do it this way, it's easier. And P times and VP over V. Oh my goodness, I do wrongly. Vs over Vp. Okay, now let's put in the numbers. Number of turns here, 450. Okay, 450 multiplied by secondary, which is 300,000. Okay, divided by 25,000. Okay, now we can put everything into the calculator. We should get 5,400 turns. Okay, of course, this one is already in 2 single figures. We leave it as it is. Okay, number of turns should be 5,400 turns. Okay, so as long as you give this equation, you get your first mark, and if you get the correct answer, you get your second mark for this full 2-mark question. Okay, all clear, yeah? So once again, I'd like to ask the oh, no questions. Thank you, Narayan. No questions so far. Let's continue with question number 9 and 10, the final 2 questions for our session tonight. Okay, so let's move on to question number 9. Number 9 asks you about strontium 90. All right, it's a radioactive isotope with 38 protons and 52 neutrons. 38 protons, 52 neutrons, okay? And strontium-90, right, decays, all right, it decays to form an isotope of yttrium, emitting beta particles, all right? Beta particles, you know what it is, right? It's electron, right? So electron, huh? Okay, so suggest how the nucleus of a stable isotope of strontium differs from a nucleus of a strontium-90. Explain your answer. Okay, so maybe okay, so usually, right, for a stable isotope of a certain element, right, compared to a radioactive uh isotope of the same element, for something like strontium, which has only 38 protons, right, you see over here there are 52 neutrons in strontium-90. In normal strontium, I'm not very sure how many it is, but from what I do remember, most atoms, most nuclei have very similar numbers of protons and neutrons within this range. So a suggestion we can say is radioactive nuclei usually has more neutrons. That's my point. Yeah, right. Radioactive nuclei usually has more neutrons. All right, and the explanation is because, okay, a stable isotope, all right, usually has fewer neutrons. Okay, fewer neutrons. Okay, so pretty much just need to take note, for most stable atomic nuclei of around 30 to 40 neutrons or so, the number or 30 or 40 protons or so, right, the number of neutrons should be just very similar to the number of protons, so it's usually much lower. Okay, and radioactive nuclei usually means it has much more neutrons in that nuclei. Okay, right, doing that, having a good suggestion and a corresponding explanation will give you your full 2 marks. Okay, right. Now let's move on to A part 2. A part 2, right, wants you to complete this equation, Euclid equation, for the decay of strontium-90 to yttrium. So as we have seen earlier in our question, right, it decays to yttrium by emitting beta particles. Okay, so beta particles is simply an electron, fast-moving electron, right? So electron, generally speaking, has, an electron probably has a negligible mass and a charge of -1. So let's write that down first, okay? -1 and 0. Okay, so let's find out what is the mass, the atomic mass of yttrium, this particular isotope of yttrium, and also the atomic number. So yttrium, because you see, right, 1 is -1 here, we must +1 in yttrium to balance this out. So this would be 39. Okay, and the mass remains constant because a beta particle has negligible mass, so the mass of this should remain as 90. Okay, so for these 2 marks, 1 mark for the correct numbers on yttrium and 1 mark for the correct answers for the beta particle to get your full 2 marks. Okay, pretty straightforward, yeah? Okay, so part 3. Explain why scientists limit the amount of time they are exposed to radioactive strontium. Well, if you expose to radioactive, sources for too long, you can damage yourself. You can even, you won't like it, but it is very dangerous and can be fatal, right? So, because beta particles are ionizing, so what they do is ionizing particles get into your skin. It can do funny things to your DNA, and it will ionize your DNA, and it will be not very nice. Yeah, it damages the human cells. So pretty much we can say beta, oh dear, okay, beta radiation, okay, is ionizing and harmful, okay, as it ionizes, right, and damages, right, human cells. All right, so pretty much very straightforward. You do not want to be exposed to strong radioactive sources simply because radiation, like beta radiation, is ionizing and it ionizes and damages human cells. So 1 mark is awarded if you write right that ionizing radiation is harmful to humans, and another mark is if you mention that beta particles are ionizing. So having this right will give you your full 2 marks. Okay. Now let's move on to part B. Okay, and part B, we also see here that yttrium itself is also unstable, and a scientist will put this sample of yttrium near a counter of radiation. And this table over here shows the count rate. Right. So how many counts per minute recorded by the detector as the sample decays over time. So as you can see over here, the time is in hours and the count rate is counts per minute, right? And this experiment takes place in 400 hours, right? So that's a long time. And of course, when you have a table of values, you can plot a graph. And this shows a graph of count rate due to yttrium against time. As you can see, it's a downwards curve like that. Okay. So what we need to do, we need to use figure 9.1 over here to determine the half-life of yttrium, and we have to show our working. Okay. So let's take a look here. So we have to show the half-life of yttrium over here, alright? So let's use this, okay? Count rate due to yttrium is counts per minute. And so from the start we have 48, right? 48 counts per minute is the initial, right? So at half-life, right, the count should be halved. So at 48 is the initial. So at half-life, the number should go down to 24. So because 48 divided by 2 is 24. And this is where, oops, this is where we want to draw our line. 24 is here, right? So 24. So this is our, oh dear, that's bad. Okay, 24. Like this. Okay, this is our line over here, and this is our half-life. Okay, there we go. And draw all the way down like this. Oh, this is not very accurate, but right, let's give and take. So this is 60, 70, this is 60, 64, 68, 72, 70, 72, 76, and 80. This is somewhere right between 72 and 76. So let's call this 74, okay? So basically what we need to do here is, right, the half-life, okay, whoops, me. So basically the half-life, okay, of isotope, of the radioactive isotope, which will be equals to time taken, right, for the count rate to drop to half of original. Okay, so we need to, that's why I drew the point at 24, because, right, so count rate at first half-life, okay, at first half-life, oops, be equals to 48 divided by 2 should be equals to 24 counts per minute, okay? Which is why we did that. So from graph, right? Ooh, I always keep writing that. Half-life of yttrium to be equals to, let's see over here, 74 hours. Okay? Now we just write it down here. 74 hours. Okay? So this is a 3-mark question. How do you get the full 3 marks? Firstly, we determine the count rate at the first half-life, which is 24. This is your first one. Okay? And your second mark is when you write a number between 72 and 76, which is 74 here. 1 mark. And your third mark is if you do the proper workings on your graph over here. So you draw a nice straight line down here at 24 and a nice straight line all the way down here, which is right here at 74. Doing so should get your full 3 marks. Okay? So the last part, C part 2, they want you to explain, right, the difference between the count rate in table 9.1 and the count rate due to yttrium being plotted on the graph. So as you can see, we have a time and the count rate of 68 over here, but on our graph, we start with 48. What's happening over here? Okay, so the value on the graph is lower than the value in the table. But here's the clue, okay? In the graph, it's stated here, count rate due to yttrium, counts per minute. In our table is recorded time count rate, which is counts per minute. So I'm very sure in this table, right, we did not take background radiation into consideration. And that's the reason why the number that's recorded in the count rate, which is 68, is higher than the number that was given over here in the graph, which is 48. All right. So with that knowledge, let's write it down. Okay. Explain the difference in the count rate and in the table and the count rate in the graph. Okay. The count rate in the table, all right, includes background radiation. Okay, while the count rate in the graph is only for yttrium. Okay, this is straightforward, yeah? Okay, good. Now that that is done, so far no questions. Fantastic. Let's move on to question number 10, which is our final question for tonight. All right, let's move on. Okay, so question 10. Now, my favorite part, astronomy, Jupiter and Earth, right? So if you are looking through the sky to in the next few nights, right, Jupiter is low above the western horizon. If you can take a look at it, it's a nice bright star. It's a nice bright star you can see through with your naked eye. All right. So Jupiter and Earth are planets in our solar system. Well, duh. So describe the composition of Jupiter and the Earth. And from your textbooks and from the videos that you have learned, right, you do know that Jupiter is a gas giant and the Earth is a rocky planet. So, simply put, Jupiter is made up of gas, and so Jupiter is gaseous. Oi, 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 oi. That was a horrible spelling. Gaseous, while the Earth is rocky. Right? So remember, Jupiter is a gas giant, so of course it's made of gases, and thus is gaseous. The Earth is made up of minerals, rocks, and thus it's called rocky planet, right? We have the inner rocky planets and the outer gas giants. Yeah? Okay. Right, fantastic. So let's move on to part B. And in part B, the gravitational field strength at the surface of the Earth is approximately 9.8 newtons per kilogram. And the gravitational field strength at the surface of Jupiter is approximately 23 newtons per kilogram. So define gravitational field strength. I'm very sure you guys have not learned this before, but let's take a look at the units, right? The clue is at the units of the gravitational field strength. So you see, right, it is newtons per kilograms. So pretty much gravitational field strength is the force exerted per kg per unit mass, right? So define gravitational field strength. Okay. Gravitational field strength is defined as, right, the gravitational force, or should I say weight, right, per unit mass, okay, of an object. Okay, right? So if you write this, right, gravitational field strength is defined as the force or gravitational force per unit mass of an object, you get your full 2 marks. Okay? So we are to state one factor which causes the difference between the gravitational field strength at the surface of Jupiter and the gravitational field strength at the surface of the Earth. So as you can see here, Earth is 9.8, Jupiter is 23. Jupiter is much greater than Earth's. Why is that so? Gravitational field strength pretty much dictates, right, is dictated by one, okay, the distance, right, where you are from the basically it is also where are you standing on the planet. So Jupiter is, of course, as you know, is much bigger than the Earth, right? Okay, but here's another catch, right, is that Jupiter is also much more massive than the Earth. So the two factors are the distance away from the center of the planet and the mass of the planet itself. So the one factor that causes this is not the distance away, not the radius of the planet, but instead the mass of the planet. The mass of the planet is the factor which causes the difference between the field strength at the surface of Jupiter and the gravitational field strength at the surface of the Earth. So, Jupiter's mass. Right. Is much more massive than the Earth. Okay? Right, so pretty much, I'm going to teach something a little bit out of syllabus, but let me show you. As I said before, gravitational field strength is equals to, right, gravitational constant multiplied by the mass of the planet divided by the radius from the center of the planet, radius of the planet, right? Okay, so of course, radius is of Jupiter is greater than Earth, but the mass of Jupiter is like much more massive, and that's why mass is actually the key why, you know, Jupiter's gravitational field strength is stronger compared to Earth's. Okay, now that's done. Oops. Now that's done, let's move on to the next part, which is part C. We are to state and explain the difference between the orbital speed of Jupiter and the orbital speed of the Earth. Alright, so as you do know, Jupiter is the 5th planet from the Sun, right? Earth is number 3, Jupiter is the 5th. And Earth takes 1 year or 365 days to orbit the sun, while Jupiter takes 11 point something years, almost 12 years to orbit the sun. So Jupiter is much slower. Orbital speed is also much slower than Earth's. So let's write that down first. And why is that so? Because, right, we do know that, right, orbital speed is given by this equation. V is equals to 2 pi r over t, right? And t is time, okay? R is the radius from the sun, okay? And v is the orbital speed, right? We do know this, okay? And so, as you can see over here, let me just write it down nicely, okay? So if your distance is greater away, right? Okay. Oh yeah. Wait a second. 2 pi r over t, right? So your okay. So of course, when this goes up, the time basically, let's say this is Earth, right? Earth is low, right? This is low. This one is also low. So velocity is up, right? It's faster. But when you're in Jupiter, where this is higher, the radius from the distance from the sun is high, is very far away, the time taken is very, very high, then the velocity is much lower. Okay, so because Jupiter, right, it's further away from the sun. Okay, thus, right, the gravitational field strength of the sun, okay, is weaker compared to the Earth. Okay, sorry. Jupiter is much further away from the sun, right? And thus the gravitational field strength of the sun, okay, so we say there is weaker than the field strength at Earth. Okay? Right. So, writing that Jupiter's orbital speed is lower, this is your first mark. Jupiter is further away from the sun, the second mark. And thus, gravitational field strength of the sun at Jupiter is weaker than the field strength at the Earth, is your third and final mark. Okay? Yeah, so pretty much just like that, we are done with the paper. We are done with today's paper. So once again, if you viewers, if you have any queries, right, you can feel free to ask in chat, right? I think we don't really have much people left today, but that's fine. Let's just call it a day. All right, so since there are no other questions, okay, no other questions, let's wrap things up for today's session. All right, so there we go. Okay, temporarily, and there we go. All right, so now that we are done, thanks everybody for joining us for this paper solving session. So for the students who have solved this paper together with us from the start to the finish, right, I hope this video helped to use the method to see the methods and tricks that are used to solve these questions, and it will help you to solve more papers like this in the future. All right, so now before we wrap everything up, let's special mention to our website here, Homeschool.Asia, which is do check out their YouTube website. And also, if you are interested, please go ahead and go to our website. Wait a second. Give me a second. All right, give me a second. Okay. Hi. Okay. So, before we continue, right? So first thing first, let's special mention to Homeschool Asia. Basically, yes, I'm on, right? Okay. Sorry about that for the scuffle. Please go to Homeschool Asia if you want to have a most comprehensive, syllabus for IGCSEs and the A levels. We have physics, biology, A and E maths, chemistry for IGCSEs, and we also have the same subjects for the A levels. And for the A levels as well, we have accounting and economics. So each subject has almost 100 videos or more, right? And teaching you each individual topics in detail, how to solve difficult questions found in examinations. As well, we have a mountain of resources such as self-generated test papers and revision notes to help you achieve that A in the subject you want, right? As for this paper, right, paper 4.1 from 2035 summer, right? Please go ahead to ciepastpapers.com, right? ciepastpapers.com, where our latest past year papers from Cambridge are available for free. And do visit to download more papers there for your reference and for you to practice. All right. And finally, last but not least, I'd like to thank all my supporting staff and also our teacher, Narayan sir, and the team for another successful stream. Now, with that said, wishing everybody good night, good evening, good afternoon, or morning to wherever you are, and all the best for your examinations, which is coming very soon. I will see you in the next video. Bye bye.